Hi, good morning. This is Mr. Michael, a professor in Aksum University, Ethiopia, and today I'm going to talk about the next topic, and this is entitled bracketing methods. This is actually the second part of the course, and this second part will talk about more on roots and optimization. So the first topic, which is bracketing methods, it will um, it will determine the roots of some functions numerically. So the objectives of this um, topic is first is understanding what roots problems are and where they occur in engineering and science. Okay. So many times that we encounter solving the roots of an equation, probably in mathematics, but how do we apply this in reality? Next is knowing how to determine a root graphically. This is the well, this is not really part of the numerical methods, but we can estimate the root if we know the graph. Next is understanding the incremental search method and its shortcomings. So there will be a program, and then we will see what is this incremental search method. How does it determine identifies that there are some in this boundary, there is the root of this particular function. So we will see that one. Next will be knowing how to solve a roots problem with a bisection method, which is the first topic in bracketing methods. Another thing is knowing how to estimate the error of bisection and why it differs from error estimates for other types of root location algorithms. We will see this one. And lastly, we will know what is this false position and how it differs from bisection. There is another bracketing method, we call it false position. So in this lecture, we'll talk about the bisection and false position method. Alright, so roots problems occur when some function f can be written in terms of one or more dependent variables x, where the solutions to, well, f of x equal to 0 yields the solution to the problem. Many areas in engineering that we want to determine this particular variable, so sometimes we write it explicitly, but there are times that we cannot do that, and then we can write it implicitly. So these problems often occur when a design problem presents an implicit equation for a required parameter, and when the equation becomes implicit, which is quite difficult to solve, we cannot do it easily in the normal mathematics analytical solution, and that's the time that we need numerical method to solve these particular functions. So one thing in knowing the roots of the equations or roots of the equation is that graphical method. So this is a simple method for obtaining the estimate of the root of the equation. So you simply have to plot it. We learned already how to plot in MATLAB, how to make a function, how to make some array manipulations, and then we make a graph, we plot it, we can use Chapra, whatever, and then from the plot that we've seen, we can see that the behavior of the plot will be something like this in your screen right now. First is graphing the function can also indicate where roots may be and where some root finding methods may fail. Okay, for example, in this case, and the first one, letter A, type A, same sign, no roots. So I mean to say here that f of xl, if you have two brackets, your lower x, so xl, call it xl, and then xu will be your upper root. So if this the function f of xl and f of xu are the same, meaning to say they have the same sign, in this case they are all positive, then we could say that there is no root, like in this example, wherein you can see that this function does not cross in the x-axis. Okay. Next one will be different sign, one root. So most of the time we will do most of this kind of problems. F of xl somewhere here that is negative, xu is positive. So if there's a different sign, meaning to say that our intuition will tell us that there might be one root inside this bracket. Another thing is same sign, two roots. So here you have the same sign, and then as you can see, the root intersects twice in the x-axis. So f of xl and f of xu are all positive, and there is a possibility that there are two roots. Okay. And lastly, different sign and then three roots. So based from this analogy, we can say that if the f of xl and f of xu are of the same sign, there might be no root or even roots. But if they are of different sign, there could be even roots, one root or two, three or five, whatever. So these are the possibilities that we can do. So by plotting the function, you can just simply see what is happening there in the graph, and then from there you will know the roots. But there's a much better way, and that is the numerical methods that we will talk about, which is the bracketing methods. Like I said, bracketing methods are based on making two initial guesses that bracket the root that are on either side of the root. So the first thing that you will do is you should have two x, okay? That is, you have the lower x and then the upper x, and then you will guess whether there is a root in between. Brackets are formed by finding two guesses, xl and xu, like I said, and where the sign of the function changes. That is, where f of xl times f of xu, so that is multiplication, is less than 0. If that happens, it means that like I said in the previous slide, that there could be one root or might be three roots. Okay, so this is very important. Now, the incremental search method tests the value of the function at evenly spaced intervals and finds bracket by identifying function sign changes between neighboring points. So this method is like it is a program. You fill it in your program, and then you fill in the function, and then this incremental search method, it will it will give you some bracket wherein there is a change of sign, and then if you that is the output, or it will return that bracket, and then from that bracket you will use some other method like bisection method, and then you will see that, okay, you test this bracket here, what are the roots and whatever, something like this. This is the incremental search method. Okay, so okay, like but there are some problems. We will talk about this one, incremental search hazards that we will be encounter in the future. But most of the time we will not use this one, because as an exercise we will just use our intuition to give us biographical method. We can provide the XL and XU, the boundaries, the brackets, but in reality you need an incremental search method for your program, so that you will know how many roots are in the function. Okay, so if the spacing between the points of an incremental search are too far apart, then brackets may be missed due to capturing an even number of roots within 2 points. So there might be a problem that the roots of the equations are too close with one another, and so if that is the case, if the brackets are too far away, then you cannot, meaning to say the brackets are of the same sign, then you cannot capture those two roots or even roots. That's one of the problems of incremental search method. And another thing is incremental searches cannot find brackets containing even multiplicity roots regardless of spacing. It means that if you can remember in a very simple quadratic equation, okay, for instance, we will write this one. If you could remember in any, let's say ax squared plus bx plus c, for instance, equal to 0, and we know that to determine the roots of this function, simply we write x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, and there are three possibilities. Now, if this discriminant is equal to 0, so if b squared minus 4ac is equal to 0, therefore there are two roots. They are the same. They are equal roots, two equal roots, and This is one of the problem in incremental search, because if the roots are equal, for example, xr is equal to x1 and, well, this is x2, the incremental search, it will just tell you that there is one root which is equal to that, well, whatever the value is. But without that one, I mean, the incremental search will not tell us that there is two roots here of the, I mean, equal roots, two equal roots. So it's one of the problems also. Okay. Now, looking on the graph here, this one is a graph. For example, here in the first one, boundary xo and x1, there are two roots. So if your boundary is xo and x1, for example, that is the incremental search, you fit in the boundary, your distance is too high, then you cannot, you will not know that there is a root here, because your function will tell you that there is the same sign. So that is quite difficult. Another thing is there are two roots here somewhere, x2 and x3, but they are very close to one another. It's very difficult to know that there are two roots there if the distance are too far. For example, if you are making x2 and x3 here as your bracket, then you will never find all these roots. That's one of the problems. But if you will use this part here, x4 and x5, then x4 is a positive, maybe somewhere here f of x4, and x5, f of x5 is negative. Then based on our intuition about in the last slide, then we will know that there is one root or three roots, whatever. Even here, in between x5 and x6, you will know that there is one root, but the problem is there is a very rapid point of inflection somewhere here. So if you are using x5 and x6, you will never know that there is a root there, because f of x5 and f of x6 in this example are all negative, and so it will just return maybe no roots here, something like that. So these are one of the problems for incremental search method. So in this case, probably a graphical method will help us. Okay. But we will not dig too much about this, because, well, it might be difficult for all of us, but I'm just telling you that incremental search is a very good function that should be incorporated in any program. Now, let's go to bisection. Bisection method is a bracketing method. Okay, so what does it do? The bisection method is a variation of the incremental search method, in which the interval is always divided into half. Okay, so I think there is an example here which we will see, and I will write that one here also. So you have two intervals, and then from your interval you guess the root to be somewhere in between. Okay, so if a function changes sign over an interval, the function value at the midpoint is evaluated. Okay, I will give a very specific example here right now. After this, the location of the root is then determined as lying within the subinterval where the sign change occurs. It would be easier if we have an example here. So the observed error is reduced by a factor of 2 for each iteration. Okay, so this is an example of the bisection. There is a function, and then you are trying to guess the root. So how do you do this? Let me draw this one. So, for example, this is the function. Okay, from there, we'll just copy that one. And then I think here is 50. Okay. Then there is well, this is 100 maybe. I'm sorry, it's not drawn to scale. And then somewhere here it's 150. Okay. I'm sorry for this, it's not drawn in scale. This is m and f of m. Okay, this is f of m. And then, okay, the first, it assumes that this is xl, and xu is somewhere around here. Okay, let's just make it, well, maybe 300, whatever. Okay, so how does bisection works? So in the first iteration, for example, uh, say first iteration, you look at XL and XU. So f of XL, here, this is f of XL by the way. Maybe I will write somewhere here. And that is negative, okay? Whereas f of XU will be somewhere here, okay? F of 300, you know the function. You can determine f of XU actually, but we will just not do that here. That is positive. So this is negative, that is positive. It means that there's a test. You test first. F of XL times f of XU. If this is less than 0, then there is one root or three roots. But since this is bisection, then we will just say there might be one root. Okay, so there's a root. Now, after here, you guess the root. XR, let's say XR1, because this is the first iteration, you will say might be at the center, XL and XU over 2. Okay, so based from the drawing there, if you make like this, like that, looking on the center, maybe somewhere here. Okay, unfortunately, in the graph, it's well, maybe in my case, it's somewhere here, but in the graph, it's somewhere on the left side. So I will just copy that one for now. Okay. We can do like this. We can, for example, this is the XR here. It's better to, I think it would be easier to transfer this one a little bit here. Maybe it would be better if this is XU. Okay, for now. Okay, so it's still not good. We will move on. Somewhere here. I will assume this is XU and this is f of XU. Okay, just ignore this one for now because I just want to follow what's happening in the slide. So if this is the XU, intuition will tell you that probably this is your XR. Okay, I'm not so, this is just an estimate. Okay, so XR will be somewhat in between XL and XU. Okay, so this is my XR. Okay, so I will say XR is like this. Now, you have this guess, but remember the true root lies somewhere here. This is the true root. Or just in the previous lecture, this is the real root, this is the true value. Okay. Next, we will move to the second iteration. Second iteration. Okay. And then from here, you will test. You will see this f of xr here. Actually, f of xr1. I want to write something here. I just want to erase this for now. I will make the computation somewhere here. So now for the second iteration, I will write second iteration. But before we proceed, we will test first. Let's look at the behavior of the roots. Like I said a while ago, this is the lower boundary, this is the upper boundary, and this is the estimate of the root here. This one. Actually, this one is the XR1. That one. And this one is, this is the f of xr1 actually. Now, in the second iteration, you have to test first because you have to change the boundary. So if you look at here, if this is xr1, this is the lower boundary before, this is the upper boundary. Are you going to stay here in this boundary or in this boundary? As you can see, the good bracket should be here, okay? So there is a test that we will follow in order to know when are we going to change the boundary. So we call this one as the this one. Test is f of xl times f of xr is this less than 0. You look at that one. Now, if you multiply these two, okay, if you multiply the two, that is f of xl here is negative, f of xr1 here is negative also, that is positive. So if it is positive, let's do this one, do this test. If you multiply these two, f of xl times f of xr1, and then it's greater than 0, negative times negative, then what you will do is set, you set xl2, the next is equal to xr1, meaning here that the new lower boundary should be changed here, okay? And then after that, you compute again. So let's see what will happen. So the second iteration, like I said, you have to do this one. From here, xr2 is equal to xl2 plus xu, like that. xl2 plus xu over 2, or xu2 over 2. Anyway, the upper boundary will never change, but the lower boundary now is changed. So you have this one, xl2 over plus xu2 plus xu over 2. Now, where is that in our example? So if this is now your new boundary, this is now the new lower boundary here, because like I said, this is not the root, this is the real root, and then you continue farther. So if you make like this, do this one here, this is xr2 at the center, and this one here, this is f of xr2, and this one, this is the xr2, like that, this point here. Now, to go to the third iteration, okay, I will write here, third iteration, okay. In the third iteration, you have to test it again. Now, in this case, it's quite different because a while ago, f of xl times f of xr, negative times negative, positive greater than 0, then you set xl2 equal to xr1. Now here, the third iteration, your test is test f of xl times f of xr2. What is this? If you look at here, is this less than 0, or this one is greater than 0? Okay, look at this. F of xr2 is positive, whereas f of xl, actually this is f of xl times 2. Okay, we can do that one. Okay, f of xl2. Okay, f of xl2, which is this one, negative times positive, that is negative. All right. So it's different here now. Since this test, since f of xl2 times of f of xr2 is less than 0, then you set, you have to change the boundary now. A while ago you started here, and then you have this new boundary here, but now the test is different. The upper boundary should be changed, you have to change it here. And then you can see you are now moving to the true root. So your boundary decreases while you are trying to capture the root. So you set here xu2, set xu2 will be equal to the xr1, the root that you computed a while ago. Okay? And then after here, of course you can move on to the third iteration after that, but I mean the fourth iteration. But then from here, let's look at first the let's solve first this one. So this is from the third iteration. Xr2, and then here we divide this one, okay, from the third iteration. Okay, third iteration. Okay, so let me write this one. xr3 is equal to xl3 plus xu3 whatever over 2. Okay, this is now your new root. So if you look at that in this example, let's extend this one here a little bit. Let's look at extend it. Okay, and then this one is our XR3. Correct? This is our XR3. And then if you look at this midpoint here, this one somewhere here, this is the XR3 here. This one, that's XR3. So that point, that is XR3. Okay, that is the point. So you are moving now to the true root, and then the next boundary will be this one and this one. Okay, but anyway, we will just stop here. This method will continue knowing this test. Okay, don't forget this test. Remember here in this second iteration, if the test is greater than 0, then you set XL2 is equal to XR1. Okay, you do that. Now, if the test is less than 0, where is it here? If the test is less than 0, then you set XU2 is equal to XR1. That's what is going to happen here. And then we define here a stopping criterion. Okay, criterion. So you compute the error one by one, remembering that this one is equal to the current value minus previous value over the current value, then times 100 to make it percentage. So you test this one. For example, let's say the stopping criterion is equal to 1%. Now you compute the approximate error, not the current value. For example, right now current value is XR3 minus the XR2 over XR3 times 100%, something like that. That's what I'm saying. And then you compute that one, and then you test whether it is less than the stopping criterion. So you write here if EA is less than ES, the stopping criterion, and then you will say then stop. Okay, you stop. You have to stop because you already met your stopping criterion. Okay, so this is the basic method of this is the method really of bisection method. So the most important thing here is the test. Okay, and even this test we will also use this one in false position method. Okay, which we will talk about it after some slides here. So the bisection method, just solve the root in this manner. Just make it divide the lower and the upper boundary into 2, and then as you move to the iteration by iteration, you are moving closer to the roots. For example, here started here, and then from there you go here, the second iteration, and then this is the third iteration. So look at the root here, and then the fourth iteration will be somewhere here at such time that you will really hit that one. And then when you test this one, so everything will be okay. Well, so that's it. Programming bisection. It's something like this. This has already been attached or included in the book, and then we will just try to follow that one. But we can also make our own program. Doesn't really matter. But this program, when I saw it, is a function, name, bisect, and then the inputs are what is your function. So there is anonymous function, you input the function, and some arguments, and then things like this, and then there's a while loop, so you can just read that one. Okay. Bisection error. The absolute error of the bisection method is solely dependent on the absolute error at the start of the process. So the space between the two guesses and the number of iterations, there is this like this, and this is the error delta x over 2 to the n. So somewhat the error will decrease by half, but it's a function of 2 to the n. Okay. So mean to say bisection is really somewhat slow. It's really slow. So okay, now the required number of iterations to obtain a particular absolute error can be calculated based on the initial guesses. So there is this equation here that one n equal to log 2 delta x to the old over the error. So if you, depending on the error that you wanted to achieve, you can input it there, and somewhat you can have an idea how many iterations you need to achieve that error. So if you say, if you are very conservative, you want to have 1% or less than this one, 0.5 or 0.01%, then of course, as you can see, n will increase significantly. So the number of iterations increases as you decreases the stopping criteria. Okay. False position. False position is another method it's also a bracketing method, but it's somewhat different because in bisection method, as you can see, you try to guess the root by dividing it into 2, by making it half. Okay, so and then you have the root. But the false position method is like, or in the other case, they're calling it regular falsy method. It's like you make a line, and then the intersection of that line to the x-axis, you assume that that is the root. So, okay, most of the time, false position is much faster than bisection method most of the time. But there are some cases that it's not. That bisection is much better than this. So we will talk about that as we proceed. So as an engineer, as a scientist, it's really up to you what method are you going to use. But depending on the graph, depending on the function that you can see, you will know which best method suitable for that particular application. Okay, so false position is another bracketing method. Okay, I said that one already. It determines the next guess, not by splitting the bracket in half, like I said, but by connecting the endpoints with a straight line, okay, and determining the location of the intercept of the straight line, XR. Okay. So the value of XR then replaces whichever of the two initial guesses yields a function value with the same sign as f of XR. So the conditions here in bisection method is similar. It's very similar to false position method. This test, this set, and whatever. The only difference here between the bracketing and the false position method is the computation of the root here. So the main difference is only this one. Okay. So this is for bisection method. For regular falsy or false position method, what is the difference? So what is the equation to solve for XR? We will do that. There's an example here. Okay, this is the graph, and there is an equation there, which we will try to derive that one. How to derive that? Okay. So the equation is this. It's not that difficult to memorize. We can just memorize it actually. But if you want to ask how does that equation pop out? Why it becomes like that? Not like this, of course. We will do that. Okay, let me erase this first. I think this is space. This is just enough. Okay, so okay, so let's try to derive this one by okay. Of course, we have to draw that one. Maybe here. This is f of x. Okay, and this is x, let's say you have that function, which is just something like this. So this is your f of x, by the way. Yeah, maybe y is equal to f of x. Okay, and then this is the true root, the true root. But let's say this is your xl here, xl. Okay, and probably let's assume that this is your xu. Okay. Okay, so it will be better if we will write xl here. So this is the example. False position method. It just what will it do is it will just make a line connecting these 2 points, f of xl, and this one is f of xu. So like that, it's not so good. And this is the xr. Okay, that is the assumption. That's why it's a regular falsy method, because we really knew that this one will never intersect here. But as you as this one maybe somewhere here decreases, so by its distance, then probably the xr will be very very near, closer to the true root. Remember, this is the true root. Okay, so how does it do that one? As you can see, that is just quite simple. Look at this triangle here. There are this triangle. I will make here a triangle 1. Okay, this big triangle, and there is another small triangle here, triangle 2. Okay, as you can see, they are similar because of this angle here, same angle. Okay. So they are similar angles, and so you can write the similarity ratio. F of xl is negative. Remember, it's in downward y-axis. So you write here negative f of xl, this length and this length over that length is f of xu. Okay, exactly from here, negative xl, because this is negative, attaching negative, it will become positive. This one, f of xu, is equal to xl. This one, this length here is simply xr minus xl. Okay, xr minus xl over this side here, that's xu minus xr, and then so for xr. Okay, so it will become negative f of xl xu minus xr plus f of xl, okay, is equal to xr f of xu minus xl f of xu. Negative, positive, negative, and then solve for xr. So you have here xr is equal to f of xl here transpose minus f of xu is equal to this one transpose there, xu f of xl minus xl f of xu. And finally, dividing this one, you have xr is equal to xu f of xl minus xl f of xu over this one, f of xl minus f of xu. Okay, this is the equation, but as you look at the equations here, they're somewhat different. Actually, this is still correct, but the reason that it was written that way, because it's because of the fact that it would be easier to memorize that one, and you only need xl, xu, and then the functions of that, the f of xl and f of xu, and then that's all you need. You need only two unlike here, xu, xl, and but actually it's almost the same. Anyway, to do that one, we do like this. xr, copy this one, xu f of xl minus xl f of xu over f of xl minus f of xu, and then what you will do here is you will add and subtract, plus xu minus xu. Okay, So the effect here will be somewhat the same. So, and then you combine these two, this one remains the same. So you do like XR, put it here, XU, this one combined, you got what plus XU, f of XL minus XL, f of XU, and then over, minus, put here, we'll erase this for a while. Okay, so minus here XU, f of XL, and then plus XU, f of XU, all over this denominator like that. So I think they are just the same. And then collecting terms, simplifying, you will see that this one should be this is cancelled out. And then this one, you have XU plus this one, as you can see, can factor f of XU, you have f of XU times XU minus XL over f of XL minus f of XU. And then to make it correct for that equation, what you will do is you attach a negative sign here, multiply by negative 2. So it will become XR is equal to XU minus f of XU XU minus XL, and then here, since you put negative sign, it will be reverse. It will become f of XU minus f of XL. Okay, and so this is now the equation for false position method. So the steps will be the same there in bracketing method. The only difference is the equation. So why even this one or this one, it's up to you. They are just the same, but well, let's just use this one because this is the recommended equation. Okay, I hope you understand. Okay, so bisection versus false position. There are some times that, like I said, false position, most of the time it's much better than bisection method. We can try that one, we can solve a problem later, and then we will see what's the difference between these two. But most of the time, false position is much faster. But the thing here is there are some cases that false position is quite inferior compared to bisection. Bisection does not take into account the shape of the function. That's one thing which makes bisection much a little bit, which is not that good, because it does not incorporate the function. It just divides it into two and then guess this root, and then that's it, whatever the function is. False position, because there is the function, it will know. It incorporates the shape of the function. But in this example, false position is bad in that example. So what is this graph? Let me see. So that is a graph. If the graph will be something like this, there is a big problem for false position. It will converge, but it will take you so many iterations. Maybe, I'm not so sure, 20, 30 iterations. But for bisection method, I think it will just less than 10, or maybe 10. You can do that one. That is one of the problem for false position method. That's why in this lecture, we as an engineer, as a scientist, it's better that you have to plot the graph first, and then you try, you see, and then you use whatever function, a method that is suitable for that one or faster. But as you gain experience in numerical methods, you will know immediately what are the best method that you can use for this particular applications. Okay, so I hope you understand. That ends this lecture, and with that, thank you.